And now from this point on, everything I say, as long as I'm close enough to the computer to pick up the microphone there to pick it up, and everything that's projected on the board will be recorded. Now all my arm waving, that won't be recorded because it's not being projected. Okay. And let's start with the current slide. And this is where we got to last time. Okay. And if you have a book, and I don't see that there's only probably one or two that do have books. Do you have one, Jack? No, okay, you're using the thing. And by the way, the syllabus goes in, went into fairly great detail on the syllabus if you watch the video. I know that, I'm guessing that most of you who are not Lawson students, which is most of you, probably are using a book other than this one for your calculus sequence. Am I right? Okay. So, if you want to use your own book, just find the chapters that correspond to this, do exercises out of those chapters. All these books are so similar. I've taught from a bunch of them, and there's not hardly a dime's worth of difference in most of them. The reason I use this book, I know Bill doesn't like it particularly, but what it has that most books do not is it has some internet resources. One is larsoncalculus.com. That's a free website. Anyone can go there, no passwords required. You just go to the website, and there's certain problems in here. In fact, the one we're going to start with today is one that's example 4, where we're going to start today on page 447. I said 446, but it's 447. It says, see larsoncalculus.com for an interactive version of this type of an example. So you've got that on this. It has videos explaining concepts of interactive examples, that's what we're talking about. Videos explaining concepts of calculus. Three-dimensional graphs can be viewed and rotated. You might need something special there, a Wolfram's free CDF player, whatever that is. Videos with Bruce Edwards, who's the co-author of this, the second author, and editable, those that miss lunch, editable spreadsheets of the data sheets for the text. Second thing it has is calcchat.com. Free website, completely free. Anyone can go there. Your grandmother can go there. She doesn't need to be in the course or anything. That, when I assign the homework exercises, I always assign certain ones out of odd number exercises out of each group in the back end of the section. Okay? Okay. Number 1, try to work the homework exercises, the ones that you choose to work. That's up to you. Try to do those. When you get an answer, look in the back of the book. The odd number answers are back there. If you get the answer, you're fine. Go on. If you did get the answer, see if you can figure out where you made your mistake and get it correct. If you can't figure that out, don't get frustrated. You don't have to wait till the next class to ask me a question. You can go to calcchat.com, and that offers students the solutions to the odd number exercises in the text. Every one of them, as far as I know. When the solutions are not enough, they can chat with an online tutor for live help. Okay? So visit the website for the tutor's availability. They won't be there 24/7, but they'll be there at certain times. Okay, now in most of the groups of exercises, okay, all the odd ones are at CalcChat, but in certain groups of exercises, one may be designated with a red number in the text. You know, like it's 17. If it's red, but all the rest of them are black in that vicinity, then that is at calcview.com. And again, it's a free website, but you don't even have to type that in. If you have a cell phone that will read a QR code, you can just read the QR code near that, and it'll take you right to that example. Okay? And that gives you it's a video solution, not just a worked out solution, a video solution of those selected exercises. There's only going to be one per little section there. And you watch calculus instructors progress step by step through the solutions, providing guidance to help students, blah, blah, blah. I don't know of any other text that has those three features. Absolutely free. Now, Cengage also uses WebAssign as a homework platform and stuff. I think ultimately I have to do that, especially if any of you are going through the Cengage Unlimited and doing that. For you to access the ebook, I think I have to be logged onto that. So they will pick out exercises and put them out there. I don't assign those, but you might find them helpful. I found out last term that I had 4 baseball players, sadly, in my pre-calculus algebra class, and they had so many games, especially last term, that were during class time, you know, either away games or home games that were at class time, that they had to be over there. And they said they used the videos that I did, you know, but then they also used the WebAssign because it has tutorial help and stuff like that. All 4 of them did pretty well in the course, to have missed as many days as they had to miss. And they said the WebAssign really helped. So it will be out there. It's not out there now, but it will be out there at some point. I don't know when. And as soon as I can get it there. Sometimes they're really slow at Cengage getting the thing set up, but I'll try to get that done. All right, but those are why I use this text. Okay. I can't think. Any questions? Any nature? Okay. All right. Where we were, now this says example 2. We've already done example 2, and we've done example 3, but you see the slide set doesn't contain all the examples in the book, so when there's not, you see here's example 2 worked out, and it goes straight to integration as accumulation process, which is a couple pages away. So I go back here, and this is where we'll work on example 4. Okay? So let me get my pen set up. Well, it didn't take. Okay. All right. And example 4 is one of these that is at larsoncalculus.com for an interactive version of this type of example. Find the area of the region between the graphs of f of x is equal to 3x cubed minus x squared minus 10x and g of x, which is minus x cubed plus 2, no, that's minus x squared. I have a cataract that is bothering my reading, and sometimes I misread pretty badly. So that's a minus x squared plus 2, and that's why I'm having to squint at the page. I think that's 2x. Yeah. Okay, make sure I got it all right. Okay. We want to find the area between the regions of the graphs, of those 2 graphs. What do you reckon we need to do to determine that? Where would you begin? Ah, okay. In other words, we're going to have to graph it, aren't we? Okay, so let's set to do that. I'm going to cheat a little bit, and this is going to be awfully crowded, I promise you that. Let me see what ranges we need to deal with here. They say from minus 10, so this will be minus 5, minus 3, minus 2, minus 1, okay, minus 4. Okay, something like that. It's not very evenly spaced. I'll try to do the same thing here. In fact, that's really lousily spaced, but anyway. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we won't need that many up there. Okay? I'm cheating by using this. Obviously, these are not to scale. This will be minus 2, minus 1, 1, and 2. Obviously, the scales are different. Okay. So, give me a few points where you want to begin. I love it. Okay. let's do f of x in this color. So what would that be at 0? Where are we? 0, 0, okay. Give me another. You want to go and do the other one? Well, let's just do all the f's first. Okay, f will be in this color. Give me another x. Say again? 2. Okay. 2 cubed is 8 times 3 is 24 minus 2 squared is, say again, 4, and that would be 20 then, minus 20 again, that would be a 0. So x equal 2, we're at 0 again. Y'all are a bunch of 0. I mean, no, you're choosing, never I go. Okay. Give me another x. 1, okay. That's pretty easy. What would that give us? Minus 8, is that what you said? I knew you did. Okay. Minus 8, okay. Just add the coefficients. 1 is really easy, right? Okay. I hope I did it right. All right, and give me another one. 5, is that what you said? Please don't say 5. We're only going minus 2 to 2, okay? Negative 1, okay. What would that be? Negative 1 cubed is? Negative 1 times 3 is? Negative 3. Minus 1 is negative 4. But then that's a plus 10 will be a plus 6, I believe. 1, 2, 3, 4, 5, 6. Somewhere about there. Agreed? Okay. And next. Negative 2. Okay. At negative 2, that would be an 8. That's 24 minus 4 again. That comes out of 0 again, doesn't it? Yes. Well, does it? I believe it does. No. No, it doesn't. I knew it didn't. Can't possibly. Okay. Not there. Whoa! I lost too much. Okay. Let's do it more slowly. That would be a negative 8. That would be a negative 24 minus 4 is minus 28 plus 20 is minus 8, I believe. Okay. So, we won't go any further. So you know it's coming up here somehow like this and going down through here. I don't know that's the minimum, but we'll assume it is something like that. We'll say it's looks like that. And that's about right for a cubic graph of a cubit, right? At most 2 changes of things, so yeah, we got it. 2 humps. All right, let's do the G. What color you want G to be? You pick a color. Second? Red? Is that what I heard? Okay, red. All right, I'll try to get red to come up. There it comes. All right, give me some points for G. G is in red. 0. And what would that be? 0, 0. Okay, right on top. The line should go through it. Okay, next. 1. Okay, when X is 1, what is G? It's what? It's 1, isn't it? That would be 1 squared plus 2 would be 1. Okay. Give me another. Give me another X. 2. Second? 2. 2? Is that what you said? Okay. I'm hard of hearing, so sorry if I have to make you keep repeating something. What would that be? When X equal 2, this would be, all right, 0. Okay, good. Next. Anybody? Second? Negative 2. What would that give us? Negative 4, is that what I heard? Or is it negative 8? Negative 2. Yeah. Okay. Okay, when X is negative 2, right? That would be negative 4 plus a negative 4 would be negative 8, right? All right, good. I thought someone was saying 12. Okay, next. -1, what would that be? Okay. -3, is that what you said? Yes, that's it. Okay, I can't hear. All right, now this looks like it's going to be, and of course, since we all know what a quadratic gives us, is a parabola, right? So it's going to be a long sloping parabola here. Now, the reason it looks so weird is because our scale, x scale, is expanded and our y scale is compressed. But that's how it looks. All right, now what does that tell you? Second?
The g of x is the upper limit.
Okay, g of x is upper limit on this part, but f of x is the upper limit on this part. So we've got two integrations we've got to do, because we want the area in between. If you just did from here to here and did your division up, you're going to have this being, depending on which one you put on top. If you put g on top, you get a positive value here and a negative value there. You're going to get something probably pretty close to 0, and that's obviously not the area. Okay, so you're going to have to do f on top here and g on top there. Okay, so let's. This is going to be ugly, isn't it? It's already pretty ugly. All right. So our integrals will be what? What limits? Okay. If you haven't figured it out yet, we're going to do our dx's, right? Do our little rectangles here. And the width of these is dx, or delta x if you were trying to be precise about it. And the length is going to be f minus g here. Whereas over here, and I'll go and change colors here so we can, well, yeah, I will, okay. If in here, then your dx's will be your width, and your length will be g minus f, okay? So where will these be, how will these play out? Let me get my color back. What's the first interval? From -2 to 0. Those are the limits on our x. Since we're using dx, that's what we measure. The limits will be on x. And what will it be? Okay, it'll be the 3x cubed minus x squared, if I can read my writing under there, minus 10x minus the g. Now, if you don't mind, I'll go on and do the subtraction as I go, plus x squared, because minus and minus is a plus, and minus 2x dx. Everybody buy that? Okay. I'll put it in parentheses so it doesn't have to be. The next integral will be, let's go on and do this in red since it's so much fun. Okay. Not to change colors, but maybe it'll help you see better. Next integral will be from 0 to 2. Problem with the red, you can't see it up there, okay. And what would be that integral? The integrand. You're saying minus x squared, is that what you're saying? The g, yeah, minus x squared plus 2x. My writing is getting very slow. Then we're going to subtract the f, which is going to be minus 3x cubed. And minus a minus is plus x squared. And minus a minus again is plus 10x. And then the dx. And you can put that in parentheses too if you wish. All right. Now let's simplify before we start integrating. You okay with that? All right. I'm going to try to fit it in here. That'll be the integral from -2 to 0. The pen is really slow. And by the way, this is an ionizing pen writing on the screen. Have you ever signed out at Home Depot or something with those pens? You know how much it looks like your signature. So forgive my writing stinks anyway, but it's even worse with this. Okay. So let's do what we got here is a 3x cubed. That's the only cubic term. And you have a minus x squared and a plus x squared. They add to 0. That's pretty nice. and then you have a minus 12x. So that's going to be our integral here for the first one, plus, and then let's go back to red, not that we have to, it's just sort of fun to do. Okay, plus the integral from 0 to 2 of, let's move the minus 3x cubed in front, and then we got a minus x squared and a plus x squared. Look at that, those go to 0 again. They don't like, for some reason, okay, finally, yuck. Yuck. Okay. Where did it go? There it is, okay. I lost it for a minute there. The x squareds go out, and then you have a plus 12x, which is exactly, surprise, surprise, the opposite of that one, which you get from subtracting each other from each other. So, and that's your dx. So now we finally get around to integrating. So let's do the first one, and we'll come down here with it, somewhere down here. What's the antiderivative of 3x cubed? Anybody? 3x to the fourth over 4 minus, next, this one right here, 6x squared. Perfect. Can I continue in blue, or do you want me to go back to red? Will it be easier to see, huh? I can't hear. Keep it blue? Okay. Okay, the next one will be same integral. Oh, whoa. You have to put the limits there. That'll be from minus 2 to 0. And then we have the minus, well, wait, I think it might be helpful. I tend to skip lots of steps, which I probably shouldn't. Okay. All right. So I'm going to put a plus here, and then let's put this in the bracket. Now let's do that. What would this one be? Antiderivative of minus 3x cubed. That would be exactly the opposite of what we had before. Minus 3x fourth over 4 plus 6x squared. And we'll evaluate this one from 0 to 2. Okay. Sorry, I've got such a limited board space and my drawing took way too much room, so I'm just piecing as I can. So, let's do the first evaluation there. To save y'all the effort, I'll do the 0, okay? Okay, done, it's 0. Okay, you got it. Good. Okay, so you do the second part. What will that be? I'm going to come up here to do it. When you plug in a negative 2 here, because this is a lower limit, going to be minus what's here. So that will be a minus 3, and what's negative 2 cubed? I mean to the fourth power, sorry. Say again? 16. Okay, over 4. And then, this is not coming out well, is it? Oh yeah, it's fine. Then you have the minus, because it's the lower limit of a minus here, that's going to be a plus. And then we'll plug in 2 squared, negative 2 squared is 4, and 4 times 6 is 24. Got it? It's coming back. Okay. Now we'll do a plus here. It kind of drives me nuts sometimes, but okay. Now let's plug in the 2 part here. That's going to be, I'm going to open my bracket again. that's going to be a minus, and it's going to be the same value as before. And let's go on and simplify that a little bit. 4 will go into 16 4 times, so that's going to be a minus 12, just like it was there. Okay, because it's the same numbers, it's just rearranged the minus signs a little bit. And then plus, and same as before, 24. I said 12 and it wrote only the 1, so let me get the 12. Yeah, minus 12, okay. And I'll do the 0 part again to save you the effort. That's 0. Okay, so what we have here is 12 minus, so this is a 12 plus 12 equal 24. That will be the area under the curve. Yes, the book got the same answer. Good for them. Okay. You see how it works? Sorry that it's all over the place here, but just trying to find white space is a premium. Any questions? Does it make sense? Did I lose you in moving all over the board? You okay with it? Yes.
What do you combine?
What's that?
What do you combine at the application purpose for the first one we evaluated from -2 to 0?
Yeah, that was here. This
0
one
and
here.
12.
You know what?
We got 0 and -12.
Okay. Okay. You do the 0 first, and that'll just give you 0, right? Put a 0 in here and a 0 in there, you get 0, right? Okay, I did that. Okay, so you wouldn't have to do it, okay? And then you do a minus, plugging in the -2. So the minus that goes in front of this, and put in a -2 here, that gives you your 16. 3 times 16 divided by 4, and I did 4 into 16 will be 4, so that gives you a -12. And that's where that came from. You just can't see the minus sign. No, I did it in my head. Okay, that's the -12. And then this part, remember we have a minus because it's the lower limit. So minus a minus is a plus, and then plugging in -2 here, that gives us +4. 6 times 4 is 24. So that's a -12 plus 24, that gives us a +12. Okay? Okay. And then over here, you're starting with the upper limit, and this is a minus sign here. So that would be a -12. So it's the same numbers as this. That's where I did that. -12, and this is a +24. So you get another +12 here. And both. Okay? I know it's messy all over the board. Okay. Good question. Any other questions? All right. Don't let my scratchiness throw you off anywhere here. All right. So that was example 4. Now, and it said you will get the wrong answer if you go just f of x minus g of x from 0 to -2 to 2. You'll actually get 0 as the answer, because these have a certain symmetry. Oh no, yeah, have a certain symmetry, I guess, about them. Not exactly, but you will, because we already figured that's going to be 12. This is going to be a 12. If you did them the other way, that would be a -12, so you wind up with no area. Obviously, there is area between the two, so you have to do that. So unfortunately, you do have to at least sketch some type of a thing so you get a general idea. Now, we could have come up with the points of intersection by just setting this function equal to that function. That would have given us the points of intersection without doing the graph, but you still wouldn't have known who was on top. Okay? So you really need to do the graph just to get an idea of who's on top, and then more precisely using your points of intersection from setting those two equal each other. We didn't have to, because ours came out right on the money. Okay, and just because we knew the nature of the graphs, couldn't be any others that we missed. All right, so that was example 4. Now, This is example 2 I'm having to scroll through here. Nope, we're still not ready for that. Yeah, okay. At the bottom of page 447, they introduce something else here, and they're saying when the graph of a function is of a function of y is a boundary to a region, then your graphs are going to be going vertically, okay? And then you're going to have the difference between this graph and that graph, and then it's a good idea to take a delta y, or your dy. So then you're going to go, your y will be your, the values, the limits on your integration, and you're doing dy. So they just mentioned that here, whereas in horizontal comparison, top minus bottom. When you're doing the verticals, right minus left. Okay. And if they cross, then you have to break them into pieces of the dy's. They always do right minus left. Otherwise, you come up, you lose some area, sometimes all the area. So example 5 is that kind of situation. Find the area of a region bounded by the graphs of x is equal to 3 minus y squared and x is equal to y plus 1. Okay? Now, if you're really anal retentive and have to do dx's, then you're going to have to get this y as a function of x. That's easy. This one will be a lot more difficult, and you have square roots there, you have plus or minus. It really gets to be a pain in the neck. So just go on and go with it, and let's deal with dy's then rather than dx's. So again, probably what we have to do is do our graph, okay, just to see where we're going to put things. And I'm going to cheat again and see what they go. They go from minus 2 to 1. So let's go that way, minus 2, minus 1. We'll go to 1 up here, okay? All right. And they're going to go from minus 1 to 3, it looks like. So I don't have mine drawn very well. Minus 1, 1, 2, 3. Okay? Now, I'm using what they've got in the book already, so I don't have to go it from scratch. All right, let's plot the first one. You want that in dark again? Give me a y. Second? 2. Okay, y is equal to 2. What will the x be? Well, we don't have 2. Here's a y of 2. X would be what? Yeah, but you see, since we got this one, I'm saying give me a y and I'll calculate x. Second, negative 1. Okay, x would be a negative 1. So that would be right here. 2, negative 1. Let's see if that's it. Yeah, that looks like it might be reasonable. Don't think we'll need it, but go on. Give me another y. One. Okay, when y is equal to 1, what's x? 2. Okay, so it'll be over here. Give me another y. 0. What would x be? 3. Is that what I heard? Okay, 3. Give me another y. 3. Okay. It's going to be 0, right? No. It'll be a negative 6. So that'll be somewhere way out here, okay? Off scale. Okay. I don't want to do that. Okay. Negative 1. Okay, what will that give us? 2. Okay. Y is negative 1, x equal 2. Obviously not a function of x because vertical line test failing miserably here, but it is a function of y so far. Give me another y. Negative 2. What would that give us? negative 1 for x. Okay, so it'd be right there. All right, it looks like it's going to be a parabolic form, which it should be. I don't draw well at all, but especially sideways. Okay, that's your parabola. Okay, now let's do the next one. That should be pretty easy. You want that red again or some other color? Anybody? Green? Is that what you said? Okay, we'll do green this time. Okay, and let's do that one. Give me a y. Second, 1. And what would the x be? 2. Ah, we got a point of intersection right there. Boy, y'all are good. Next. Y is equal to 2. And that would be x equal 3. Somewhere about there. Right? All right, I don't think we're going to need to go any further that way. Give me another y. 0. And what would x be? 1. I think we got a pretty good idea what this is going to be. This is going to be a line of slope 1. And it should pass through that point right there. If I had drawn decently, it would be. All right, so now we've got the area of interest. I'll go back to dark. And this is the area that we're interested in. Okay? And in order to do this, now you have two choices here. Like I said, if you're really anal retentive and want to stay with dx's, because that's what you want to do, then what you have to do is the dx's between the green line and the blue line with greens on top. But then over here you have to do the plus square root minus the minus square root. That's way too much work for me. I'm too lazy to do something like that. So let's do our dy's. You can do that, but you have to be careful and get it right. Okay? So I say, let's not do this or that. Let's do our dy's, and then you only have one integration. So let me get my pen to set up. Okay. And we'll do dy's this way. So your width is dy, your length is the first function, the quadratic function, minus the linear function. So that's what you're going to be summing those areas from. And since you're doing dy's, your integral will be, the dy is going to be in there. So what would be your range on your definite integral? Y's are going from, so from what? Negative 2 to oh no, it's, see, the portion that you're dealing with here. Yeah, you're going from here to there, the 2 points of intersection. So that's going to 1. Okay? I won't have a 0 to do this time. And I don't know why, I thought for sure I wrote down a dy, and it's disappeared. I don't know why, but let me do it again. Okay? Now what's our length? There's your width. What's our length? Okay, it's 3 minus, for x equal 3 minus y squared. That's the right hand then, minus a y plus 1, so it would be minus y minus 1. Just doing the subtraction. Does that make sense? The x over there minus the x over here. That x, this x minus that x. Okay? So let's clean that up a little bit. This will be the integral from negative 2 to 1. Okay? 3 minus 1 is not that hard. 2 minus y squared minus y. Usually I'd like to have a nicer order than that, but it doesn't really matter. The integration is going to work. dy. Okay? Antiderivative of 2. Anybody? Second? 2y. Antiderivative of y squared. Minus y y cubed over 3 minus antiderivative of y squared over 2, and we'll evaluate this from -2 to 1. Okay, sorry it keeps blinking. So let's plug in the 1 first, and what will that give us? 2. Not that hard. 1/3 minus 1/2. Boo hits, we don't have any zeros in here, so I can't do that. Then we'll do a minus. Okay, let's group these together. What would the first term of that one be? Plugging in the -2 for y. Say again? -4. Plus 8/3, is that right? Okay. Now that plus is because -3 cubed is -8, and that, okay. Next. It's still a minus though from here, because -2 squared is 4, so that's going to be a -2. Right? Now, let's clear the parentheses. That would be a 2 minus 1/3 minus 1/2 plus 4 minus a minus minus 8/3 plus 2. Taking this minus across the parentheses, distributing it across there. Alright, so what do we have here? On whole numbers, we have 4 and 2 and 2, that would be 8. Your thirds would be minus 9/3, which is a -3, right? This one and that one, right? Yes or no? Okay, minus 1/2. Okay, so this will be 5 minus 1/2, which would be 4 1/2, which I bet you the book is going to list it as 9/2. Okay, that's pretty ugly. I'm sorry about it blinking. What I have, I think, is not a great connection under here, and when I move the screen like this, it messes up the connection for my, that's going to the projector. So that's why it's blinking all the time. So let's see, we got 9/2, they got 9/2, good for them. And like I showed you, they show in the book, if you chose to do the dx's, delta x's, then you really have to be careful, because here you're doing the lengths on the y's are between minus the square root. When you rewrite this as y squared is equal to 3 minus x, and then do the square root of 3 minus x, plus or minus, this is plus the square root of 3 minus x, there's minus the square root of 3 minus x. That's what you have to do in your length here. Pain in the neck, or some other body part. Over here, then you do your y is equal to x minus 1 on top, and the minus square root on the bottom. So, sort of a pain. So this way is, I think, easier. And they do show it the other way at the bottom of the page. Do y'all need to see that? Please say no. Good. Thank you so much. Okay. All right. Now we're ready for the next part, as soon as I can scroll through this. Any questions on this before I delete it? Okay, or eliminate it? Integration as an accumulation process. And to me, yeah, this is true, but in a sense, why? I mean, it makes so much sense just doing it as an area, but it's also accumulation process, an accumulation process. Here's what they mean by that. The integration formula for the area between two curves was developed using a rectangle as a representative element. For each new application of integration in the remaining sections of this chapter, an appropriate representative element will be constructed using pre-calculus formulas you already know. Yay. Okay. Each integration formula will then be obtained by summing or accumulating these representative elements. Okay? So the known pre-calculus formula, which we'll get to in a minute, becomes a representative element, and then that will become a new integration formula. Yay. So here's what they mean by that. The area formula in this section was developed as follows. The area was the height times width, which is a delta area, would be the change of your functions. If alpha is on the top and g on the bottom, then it's alpha minus g. That's going to be the height between those two times the delta x, and that gives you your delta a. And then you sum up those delta a's from the first x to the last x of that height times that width, and the summation over all those from A to B gives you your area. Okay, that's what we've already done. So what's different here? I don't see anything really all that different. Find the area of the region bounded by the graph of y is equal to 4 minus x squared and the x-axis. And describe the integration as an accumulation process. Okay. We're going to be doing the same thing, and they're just talking about it in different terms, basically. But what is the better thing, the thing you ought to do first? Draw the graph. And I'm going to cheat again. Yeah, okay. And get my limits. So, could have done it better. I will do it better. Okay. And I think it's going from minus 2 to 2. Oh, I should have asked you to give me points and stuff like this. I'm just getting it out of the book. There it is. It's a parabola, but it's concave down because your leading coefficient is negative, so we have all that kind of information. It's going from minus 2, that gives you a 0 here, and a plus 2 gives you a 0 there. And when x is equal to 0, that gives you 4. So there's your parabola. Okay? Axis of symmetry is the y-axis. Okay. So find the area of the region bounded by that graph and the x-axis. So here's what we're interested in here. Okay, that area. How would you proceed? dx's or dy's? You tell me. Oh, for sure. Okay. Okay, we're going to do our little dx's here. So the length is, or the width is dx. The length is what? It'll come back in a minute. Okay. It's just your y value, right? So what will that length be? The integral from of 4 minus x squared, yeah, from, okay. Here I want to cheat. Is that okay? I'm lazy. I have this theory. I don't know if it's true, but it's my theory. I think that to be really good at math, you need to be a little lazy. Do any of you qualify? Oh, look at this, a bunch of budding mathematicians. Some hard workers in here too. That's fine too. You can still do it. Okay, it's fine. But the reason I say that is a good mathematician is always finding for the easiest way to do a problem. Okay? Now, I look at this, and I know because I said the axis of symmetry, even though my graph doesn't look like it, is the y-axis, the area on this side is the same as the area on this side. So why do from minus 2 to 2 when you can just do 0 to 2 and double? I like doing zeros. Okay, that's my favorite, okay, of all time. So we're going to double the area from 0 to 2. These are the ranges of x's, dx. They probably aren't telling you that yet, but why not, okay? Now, don't forget the 2 out there. And what's the antiderivative of 4? 4x minus x cubed over 3, evaluated from 0 to 2. It'll come back. Okay. So that'll be 2 times, plug in the 2, and what do you get? Help me somebody. Huh? 8 minus 8/3. Is that what I heard? Okay. I'll do the 0 part. Okay, done. Okay. And what does that give you? Second? 2 times. Now, if you change the 8 to thirds, that would be 24/3, right? Okay. 24/3, that's 8, minus 8/3 will be 2 times 16/3, and that would be 32/3. I hope. Okay, let's see what they get. Oh, look at that. Good for them. 32/3. Now, what they mean as an accumulation process, which for the life of me I don't really see why. I kind of do. There is somewhat of a region. But what they're doing, they're first going to go from from -2 to -2, which gives you 0, because there's no width there at all. Then -2 to 1, and figure that area, and then do add to that from 1 to 0, and do that area, and then add to that from 0 to 1, and add that area to it, and then so that's the accumulation process. And I think I'm way too lazy to do that much work. I mean, it's just extra calculations. Why not do it once, and even then, make it easy on yourself? So I didn't do it the accumulation process. That's what they wanted you to do. Now, the only advantage to that is in certain applications. I know none of you are fans of the bell curve, right? You hate it when your professor's grade on the curve, right? No, you sort of kind of don't mind that at all. But if you think about what a bell curve is, have y'all had any statistics? Lucky you. Okay. What statistics are, a normal curve, the area under that curve is 1. So that's all of the universe. And that is a weird function. It's minus e to the minus x squared. That's something you can't even really do an integration on it. But what you're doing is area under a curve. And that's what you're getting with the bell curve. You're doing certain percentages of your A's, your B's, your C's, stuff like the C's will be in the middle, and the B's and the B's and the A's go under here. So that's what a true grading on the curve. Most of the time they just add 70 points. That's not really grading on the curve. Grading on the, so if you're doing statistics, you're actually measuring you're accumulating from this endpoint to that endpoint. And that's what you're doing. Okay? So there are reasons where this will come in sort of okay, but you certainly wouldn't do it like this. Doing this region, adding it to that, adding it to that, adding it to this, and adding them all up, and you get that. That's just a made-up thing. And if you think back on it, the fundamental theorem of algebra, the second part of that, where you let your x be the variable, you identify it by the integral of blah, 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 in t's, but you're going from 0 to x, or a to x, that's really what you're doing. You're doing an accumulation process. But if you don't have to, why do it? Okay, this is just extra work doing this as accumulation process. Okay? No, but actually what they do, it's not quite that. They were doing here to here, then here to here, then here to here, then there to there. Why do all that and just do here to here in one fell swoop? But they're just showing integration can be thought of as that. Enough of that. Let's move on. I think that is the last slide in the set. Let me make sure. Here, okay. I wish I hadn't been doing that. Here's what they're meaning. Going from -2 to -2, that's of course 0. Because the thickness is 0 there. Okay, the height is still 0. It's there too. But then when you move a little bit here from -2 to -1, there's you're accumulating that much. From -2 to 0, you accumulate a little more. You're basically letting your bar go ride the curve up and ride the curve down, and you're adding all those together. And I look at this and say, why? What's the point? Except it's to show you can do it. So, too much said there. Okay. All right. Homework exercise is 7.1. Do any of the odds 5 through 9. They're all at Calc Chat. And 7 is at Calc View. And by the way, for those of you who have different books, you just find the section that was talking about area of a region between two curves and do whatever exercises you want there. But if you have this text, 5 through 7, they're all at Calc Chat. They all have the answers in the back too. And here's that QR code. Just take your phone and click on that. You'll get number 7 because it's the red one in this set. And that's also at Calc View. Okay? Much more illustrations of it. You know, they actually do some interactive stuff. Then do either 11 or 13. They're both at Calc Chat. 11's at Calc View. Do any of the odds 15 to 27. They're all at Calc Chat. 17's at Calc View. Do 29. It's at both Calc Chat and Calc View. Do any of the odds 31 to 35. They're all at Calc Chat. None of those are at Calc View. Any of the odds 37 to 41. They're all at Calc Chat. 37's at Calc View. Either 43 or 45, they're both at Calc Chat. 47 or 49, they're both at Calc Chat. 51's at Calc Chat. 51 or 53, they're both at Calc Chat. 53's at Calc View. 57 or 59, they're both at Calc Chat. 61 or 63, they're both at Calc Chat. There's an exploring concepts that you can choose to do or not. 65 and or 67, there should be a Calc Chat as well. 69 should be a Calc Chat. 71 should be a Calc Chat. 73 should be a Calc Chat. 75 should be a Calc Chat. 77 mentions the Lorentz curve. Now I'm not going into any detail on that, but anytime you see something like this, remember you have a paper to do. Well, you might say, well, who in the world was Lorentz? That could be a paper topic. Or how did he develop this Lorentz curve? Or why did he develop the Lorentz curve? Or how is the Lorentz curve used? Hey, who knows? You may find out it's used in your field of study. So anyway, when you see one like this, even if you don't want to do the problem, it might give you ideas for a paper topic. Okay? So 77 should be at Calc Chat. 79 is a building design type problem. That should be a Calc Chat. And then any of the odds, well, 81 should be a Calc Chat. There's a true false, a couple of those, 83 or 85, they should both be a Calc Chat. Now they also usually put a Putnam challenge here. If you're really a glutton for punishment, try that. You know, you're not going to have anything like that on the test. Those are pretty tough, I think. Okay. Now, that said, let's move on to 7.2. Okay. So one application of integration is find the area between two curves. Another application for integration is what we're about to hit here, and that's still in applications for integration, if it'll come up. That will be volume. And this time we're going to do with the disk method. Any of you hit this before already? Okay, so old hat to you, okay? I'll let y'all teach this one. Okay, never mind, okay. So, we'll find the volume of solid of revolution using the disk method, okay? We'll find the volume of solid of revolution using the washer method, which is very similar to the disk method, only different. And we'll do find the volume of a solid with known cross sections. Okay? Which is basically doing some of the same. Okay? So let's start with the disk method. Now they go into pretty much gory detail here, so let's just live through the detail here. When a region of a plane is revolved around the line, now the first one I didn't even touch it and it went out there. So what in the world is going on? It's having a senior moment or something, I guess. There was no reason. I know when I jiggle it, something could happen, but I wasn't anywhere close to it, even to jiggle or wiggle. It's my box. It's not the connection there. Well, it has to be some of both. All right. So when a region of a plane is revolved around the line, the resulting solid is called the solid of revolution. Revolved revolution, that's what it means. It's not that we're taking up arms. Okay. The line is called the axis of revolution. So if this is your axis of revolution, it looks a lot like the x-axis, but it doesn't have to be. Any axis here. And you're doing this rectangle revolved around there, what you get is a hunk of cheese. No, I mean, you get a disk. Okay? And this disk, if you're doing the volume of the disk, how are we going to do that? Well, what is volume? Volume is area times width, right? Area is a two-dimensional, width is a single-dimensional, that gives you three-dimensional volume. Okay? So the simplest such solid is a right circular cylinder or a disk, okay, which is formed by revolving a rectangle, like that little rectangle up there, around an axis adjacent to one side of the rectangle. Okay? In other words, this bottom is on the axis, you're doing around, and you get this slice. Okay? So, the width of that is W. This is the radius of this circle that you have here. So the volume is then the area of the circle, pi r squared. Now if this was the x-axis, this r would be your y, wouldn't it? How far up above the x-axis your y. This w could be your dx if that is your x-axis. So pi y squared or r squared dx or w. Pi r squared w. That would be the volume of that disk. And that's an exact slice of a right circular cylinder. Pi r squared w. Okay? Now, like I said, we're going to break these down. The volume of such a disk will be the area of the disk, pi r squared, times the width of the disk, w, where r is the radius of the disk, and w is the width. Okay, I think they've hit that to death now, right? Now, what if we're doing a curve, not a straight line, not a horizontal line around the axis, but we're doing a curve around the axis? Well, we've got problems, don't we, Houston? Okay? Because that's not going to quite be the same. But if you choose this width judiciously, or even injudiciously, I guess, and sort of hit the midpoint here, then the amount that you're overshooting here, you're undershooting there when you're, it's not the same, but it's going to be pretty close. So that's still not going to be a bad approximation of what that whole curve revolved around. You're going from A to B, so you're going to be up in there. So this, when you revolve that curve around, you get a Christmas tree stand, right? Turn this way. Okay? Now that's not going to be exact, but it's going to be close. And if you did a series of these, that's not going to be a bad approximation to what this volume would be. How would you make it better? Make your width a little bit smaller. Maybe take half of that width. And then each of those fits a little better. And then take half again. And just keep getting smaller and smaller and smaller until the delta x becomes a dx. And now you're following the curve. What's the height of that? Well, that's your function value, your f of x up here, right? So it's pi times y squared, because that's your radius, that's your area of that disk, times your delta x, or ultimately it'll be a dx. So it'll be pi f of x squared dx, integrated from a to b. The integration takes a limit as the delta x is going to 0. Okay? I just did the next several slides together. Here they're going to do it a little bit slower and more in detail. To determine the volume of this solid, consider a representative rectangle in the region. When that rectangle is revolved around the axis of revolution and generates a representative disk whose volume is delta V, that's because it's part of that delta x, pi r squared, where r is the height of that rectangle, times the delta x is the thickness of the slice. Okay? Approximating the volume of the solid by n such disk of width delta x and radius r of x of j, in other words, that's your function value, okay, produces the volume of the solid as approximately the sum from I equal 1 to n, you slice it into n equal slices, pi r x of I squared. The r is the thing squared, not the x of I. This function value squared, that value, the height there, times delta x, okay? And you can pull the pi outside the summation, pi r, because the x is in here, there's x's there, so you can't pull those out. But that will be your summation. Well, that approximation appears better and better and better as the, what do they call that? It's a delta is a symbol, but it stands for the maximum width of any of those, and there's a name for it, and it escapes me right now. Norm, the norm. The norm is approaching 0. In other words, your n, the number of increments, is approaching infinity. You can define the volume of the solid then as the limit as that norm approaches 0 of pi times the summation of your r squared delta x, r squared of x delta x. And that the summation then becomes an integral from a to b, pi times the integral from a to b of your function value, your r of x squared dx. Okay. Schematically, this method looks like the known okay, here's where they get the known precalculus formula. It's the volume of a slice, okay, and then you do a delta volume, and that, because you have just a thin slice of that delta x, okay, this is volume of any old disk. This is a very small portion where you have close to a fixed radius, okay. The new integration formula will be this. If that helps you see it, fine. To me, it's just extra work, but that's what's going on. What I do is I tend to think of this in terms of this, but not writing all this down. This is the summation, the integral of length times width. Oh, okay, area times width. The pi being out there. Okay. So, similar formula can be derived if the axis of rotation is, or revolution is vertical. In other words, the axis is here and you're revolving around here, then you've got dy's rather than dx's. Okay? So find the volume of solid of revolution. With this method, use one of the following below. If the horizontal axis of revolution going around this, then you're going to have dx's going out here, and the volume will be pi times integral r of x squared dx. If it's a vertical, then you're going to have dy's, and your r of y, that would be your length out here from the axis. If you're revolving this around like this, pi integral of r of y dy, going from c to d. They always use a to b for the x's and c to d for the y's. It doesn't matter what you call them, but they typically do that. Is that making sense? That's how you get your volumes. So let's do one. Find the volume of a solid formed by revolving the region bounded by the graph of f of x is equal to the square root of sine x. One of my favorite functions of all time, okay? And the x-axis when you're going from 0 to pi on x, which is a very good region to go, because that when x is 0, you're at 0, and it reaches a maximum of 1 somewhere out here, and when you're pi, you're back at 0 again, so this is going to be exactly that, but that's not a sine curve, it's the square root of sine, okay? And because it's positive all in there, you can take the square root in the whole region. Revolve that around the x-axis, which is what they say to do, about the x-axis, and you get basically a football, or at least a rugby ball, something like that, okay? So that's what it looks like, okay? Now, how will you find the volume of that surface of revolution? Volume of that. Volume of revolution, yeah. How would you find that? Let me get my pen set up. Okay. Nope, didn't take. There we go. Oh, it's acting much better now. I don't know why. Okay. How would you find the volume? Well, they've given you about all the hints they can right there. What would it be? Anybody? Okay, pi times 0 to pi will be your limits. Okay. Your f of x is your height here, but what are you doing with it? Squaring it. And if this f of x is square root of x, when you square that, you get, square root of sine x, you get sine x dx. Oh man, could they get anything any easier? Well, maybe a little bit, but not much. What would that be then? Pi, what's the antiderivative of sine x? Yep, you're right, negative cosine x. And that's going from 0 to pi. Okay, so that's going to be a pi. Does it feel like you might be getting a negative volume here? That would be really unfortunate, wouldn't it? Because we don't have negative volumes, do we? But what happens here? Okay, what is... Okay, you do the cosine of pi first. Okay, and what would that be? No, cosine of pi is not 0. Sine of pi is 0. It'd be negative 1. Yeah, and then a negative 1 is plus 1.
Okay, I'm thinking about 2 pi.
Yeah, right. Okay, to pi would be negative 1. And then minus, the minus, that makes a plus. The cosine of 0 is 1. So what do you have? 2 pi. That makes me hungry just thinking about it. Okay. The volume of that would be 2 pi. Okay, they're going, pretty sure they're going to show us this, but let's, oh yes, okay. All right, let's see how they do it. Whoops, I'm going to have to erase mine. I didn't know they were going to fill in there. Okay. From the representative rectangle in the upper graph of figure 716 right there, you can see the radius of that solid is going to be your f of x, the y value, okay? That's what's going around. So from there, and that's the square root of sine x, okay? And then from your formula, the volume being pi times the integral from a to b, which in our case is 0 to pi, the f of x squared, which is square root of sine x squared. That just gives you sine x dx. So this just does the pi times the integral from 0 to pi of square root of sine x squared dx, which is pi times the integral from 0 to pi of sine x dx. I'm glad they write all these steps down. Later they'll skip the most important steps, but not in this problem, okay? So that's going to be pi times negative cosine of pi, of x from 0 to pi. And cosine of pi is -1. Negative of that would be a +1. Minus of minus is a plus. Cosine of 0 is 1. So pi times 1 plus 1 is 2 pi. And that is the volume of that surface of revolution. Okay. All right. Any questions? Just like we did it. Okay. Now, they're skipping example 2. So let's go back and do example 2. Okay. Find the volume of a solid formed by revolving the region bounded by the graphs of f of x is equal to 2 minus x squared. Okay. And g of x equal 1. Okay. About the line y equal 1. Okay. As shown in the figure here. Okay. We don't have the figure, but I'll try to draw a representative of it. Okay, so here we go. Poor choice. Okay, like that. Okay. Now, 2 minus x squared, that's going to be a parabola. Vertex up here at 2, 0. That means 0, 2. Sorry, said it backwards. 0, 2. And then it'll drop down to there, and it's not going to be anything. It's going to be at root 2 here, by the way. Okay. This point of intersection is root 2. How do we know that? Because when the y is 0, then 2 is equal to x squared. So x squared must be root 2 minus root 2. Okay. Okay. Those are your points of intersection. But we're not really all that interested in that because it's also g is the function g. What color you want me to do g? Pick a color. Anybody? Yellow. Okay, hard to see, but we'll do it. Okay, g of x is equal to 1. There's g of x right there. G of x equal 1. So it's only this region that revolving around the line, g is equal to 1. So it's going to, I think I'll go back to my dark color because it's easier to see. This will be the bottom part of that thing. So it's revolved around this axis, okay, about y equal 1, which is g is equal to 1, okay. So about that. So this is the volume that we've generated here, okay. Now, here is our little rectangle, okay? What is the length of that rectangle? Say again? The length of the rectangle? It's not fixed because see here it's 0 and then it goes up like this, comes back down here. So it's not a single value.
Yes.
Say that again.
1 plus 2 minus x squared.
Okay, not quite. Do the top minus the bottom. Okay. So the length is 2 minus x squared minus 1. Okay. Which would be what? The length here is 2 minus x squared minus 1. Which would be what? Pretty easy to do. 2 minus 1 is 1 minus x squared. So there's the length of that representative rectangle. That's the thing that we're going to be squaring, right? And the width is the delta x, of course. But we're only going from minus 1 to 1. Because this part out here doesn't get involved here. Just that part. Okay? So what's our formula? The volume is equal to pi on the outside times the integral from minus 1 to 1. Is that what I heard someone say? Something like that. Okay, I thought so. Okay. Next. One minus x squared squared, right? Because you square that radius times your dx, right? Width. Anyone see something you might suggest that we do? Hence, symmetry. Yeah, go from 0 to 1 and double it. Okay, I like that. So let's make this a 2 pi and make that bottom one a 0. I like that a lot better. Okay? We're going to do half of it and double it because the volume is going to be the same on this half as it is on that half. Just by our picture here. Okay. Be lazy, folks. Okay. Now, what's probably the first thing we need to do here? You need to come up with some weird kind of formula to do composite, the integral of a composite function, a squaring function of a 1 minus. Let's just square it first, okay? Why not that? V is equal to 2 pi times the integral from 0 to 1 of, what's that thing squared? Any of you square that? Okay, if nothing else, you can FOIL it, right? Or do you know how to square a binomial? The easy, lazy way, huh? Okay, yeah, you're thinking chain rule. You like to work too hard. I'm too lazy for that.
I'll square A and then this 2AB and then B squared.
Okay, so it's 1 squared minus twice the product, 2x squared, plus the second one squared, which is x to the 4th. That it? Okay. Or you could come up here and do a FOIL of it. You know, 1 minus x squared times 1 minus x squared. That's 1 minus x squared squared, right? And you do this, that would be your 1. Then your outer is minus x squared. Another minus x squared is minus 2x squared plus x to the 4th. Okay? You get a happy face, but we're not too. Okay, never mind. All right. Let's do the integration. D is equal to 2 pi times antiderivative of 1. X minus 2x cubed over 3 plus x to the 5th over 5, evaluated between 0 and 1. This isn't going to be too awfully nasty, I don't think. I just need more room to write, so I'm going to come up here at the top. That would be 2 pi times, when you put a 1 in there, what do you get? 1 minus 2/3 plus 1/5. Okay, and the rest is just fractions, and don't we love them? Okay. Common denominator? 15. And how many fifteenths is 1. 15 fifteenths? Okay. Minus, wouldn't that be 10 fifteenths? Whoops, I can't write. And that would be 3 fifteenths. Right? 15ths. Okay. My screen's falling back on me. It's coming back. Okay. Whew. Okay. So that'd be 5 plus 3 is 8 fifteenths. 2 pi times 8 fifteenths. Okay. And that would be 16 pi fifteenths. I think. I hope. Where is it? Ah, there it is. Yep, they got it right. Good for them. All right. Make sense? Any questions on it? Yes?
So what do you choose, like, which way the rectangle goes? Like, if it goes up and down or side to side?
Okay. Depends on how hard you want to work. Okay. I chose the rectangle this way because I know this value minus this value. I know that, you know. So that's going to be really easy because this is in terms of x. That's just a number, so it could be x or y. Okay. So if that's in terms of x, I tend to want to go with a dx. Now there may be circumstances where that rule won't hold, but that is certainly one that will. If this is in terms of x, then why not make it a dx? Okay. So with that being dx, it's going to be a vertical rectangle. And the fact that it's revolving around a horizontal axis, that makes this make sense. If this were revolving around like that, then we'd want to do a delta dy because that would be slip your disk there. So that's really the fundamental reason. Okay. Good question, though. Excellent question. Any others? All right. So that was example 2. Okay. Now we move from the disk to a washer. And y'all do know what washers are, don't you? It's not the things you put your clothes in. That's not what we're talking about, okay? The washer is when you're dealing with bolts and nuts and things like this, the washer is the spacer that you have there. So that always has a hole in it for the bolt to go through. Well, that's what we're going to be dealing with now. The Zipf method can be extended to cover solids of revolution with holes by replacing the representative disk with a representative washer. So let's say we have our rectangle up here, but now the axis of revolution is not going to be on the base of it, which would make a disk, but it's going to be down here. So when you revolve this around like this, you have a hole in the middle, okay? And that forms what we call a washer, okay? Well, if you talk about the volume of that washer, then it's the volume of this disk minus the volume of that disk. Yeah, well, that's all you have to do is subtract off another volume from it. So the washer is formed by revolving a rectangle, blah, blah, blah. If little r is the little radius of the little hole, and capital R is the big radius to the big outer region of the washer, and W is the width of the washer, then the volume of the washer is pi r squared W minus pi little r squared W, which, since the pi and the W are the same, pi times the difference of the squares. Okay? So that forms sort of an easy way to define that volume. Okay? Now, that's going to lend itself pretty rather straightforwardly to what we're going to do here. Okay, so to see how this concept can be used to find the volume of a solid of revolution, consider the region bounded by the outer radius, capital R of x, the inner radius, little r of x, is shown in this figure. So here we have, if I'm not mistaken, they call this a sector of a circle. There's a name for it, where you have some secant of a curve, and the area bounded by the secant of the curve and the curve itself. Okay? Now, and that you're going to revolve around between the areas of the points of intersection there around the x-axis down here, but nothing up here is on the x-axis, so you're going to have a big washer in the middle. So this, again, looks like a Christmas tree stand, but with a really big hole here and a bigger base there. Or a megaphone or something like that. You get the general gist. So, your volume, well, let's start with the area. The height is the upper curve, which is the linear part, minus the curved part, whether that's part of a circle, whatever curve that is, that function. That's going to be the length. The width is going to be your dx, and you're revolving this thing around the x-axis, the axis of revolution is the x-axis. So it's going to be the outer volume minus the inner volume, or just pi times the difference of this squared minus that squared times your dx. Okay? And that's going to form it for you. Yes, and they don't go through summations or other things like this. We just go straight to this. If the region is revolved around about the axis of revolution, the volume of the resulting solid is, volume is pi on the outside, the integral from A to B, those are the points of intersection there, the outer radius squared minus the inner radius squared times the dx, which is the thickness of that line. Notice that the integral involving the inner radius represents the volume of the whole subtracted from the volume of the outer radius, which is the disk that was on the outer part. And that's how I usually think of it. I don't usually think of memorizing the formula, but just think the outer disk minus the inner hole, the volumes of those. Okay? So here's example 3. Yeah. Find the volume of the solid form by revolving the region bounded by the graphs of y is equal to the square root of x, which is the upper curve here, and y is equal to x squared, which is the lower curve there. And they obviously have points of intersection in common, 0, 0, because square root of 0 is 0, and 0 squared is 0, and 1, 1, because the square root of 1 is 1, and 1 squared is 1. So those are the points of intersection, with surprisingly the square root function on top and the square root function on bottom. Anything past 1, they're reversed, and the square root function is much bigger than the square root function. But in between here, the square root function is larger. Okay? This almost looks like what you might have as the shape of an airplane wing or something like that. The angle, of course. That's what you would have. So the outer function, outer radius is this one, the inner radius is that. Okay? So how would you proceed? By the way, if we get going too long and you need a bladder break or anything else, I'm always in favor. Okay? And what time is it now? About 1:25 or so? Okay, so we got about an hour left. Okay? You need a break or not? Do? Before we do this one? Okay, let's do a quick break. I'll put this on pause. All right, any questions before we get started again? All right, so here's the setup. We've just been over it. So what would be how would you go about finding that volume? You tell me. I'll put the V. V is equal to pi. Good start. The integral from 0 to 1. That sounds good. Okay, I heard a root x squared minus x squared squared dx, right? All right, good deal. Let's simplify that a little bit. What would that be? Pi times the integral from 0 to 1 of x minus x to the 4th dx. That would be pi times, what's the antiderivative of x? Second? X squared over 2 minus fifth over 5, evaluated from 0 to 1. That will be pi, and this is pretty easy math here, except for fractions. What would that give you? 1/2 minus 1/5, and the zeros give you nothing. So this will be, I'd just about as soon think of that as 0.5 minus 0.2. That would be 0.3, or pi times 0.3. Now that's probably not how the book does it, 0.3 pi. They probably say 3/10 pi, don't they? 3 pi over 10 or something like that. 3/10 pi, that's what they do. 3 pi over 10. Make sense? Any questions? All right. Good deal. All right. Well, let's see how they do it then. In the figure, you can see the outer and inner radii as follows. The outer radii, the capital R is square root of R. The inner is little r is x squared. I said square root of r, square root of x. And integrating between 0 and 1, which are your points of intersection there, would be pi times, but they say between 0 and 1 and put an a to b on it. I guess that makes sense. Capital R squared minus little r squared dx. That would be the integral from 0 to 1. There they put them in, of square root of x squared minus x squared squared, which would be pi 0 to 1, integral 0 to 1 of x minus x to the fourth, which you have already done as pi times x squared over 2 minus x fifth over 1, evaluated from 0 to 1, which they skipped all the steps this time and went straight to 3/10 pi, which is what we got to. Make sense? All right. All right, that was example 4. Okay. Trying to see where this is in the book. No, I'm sorry, that was example 3. No, yeah, sorry. No wonder I couldn't find where it was. Okay, so in each example so far, the axis of revolution has been horizontal, and you've integrated with respect to x, which is what we were talking about before. In this next example, the axis of revolution is vertical, and you'll integrate with respect to y. In this example, you need 2 separate integrals to compute the volume. And I guess they're going to show that example. Yeah, here's example 4. Okay. Find the volume of the solid form by revolving the region bounded by the graphs of y is equal to x squared plus 1, which is this curve here. See, it's a vertical shift of 1 of your regular old parent function x squared. Y is equal to 0, that's down here, the x-axis. X equals 0, that's the y-axis here, and x equal 1, that's this line over here. Okay? And you're revolving that around the y-axis. So basically what we have a cylinder with a parabola cut out of it. Okay, or paraboloid cut out of it. Okay? And which is one of my favorite volumes of all time. But that's what we've got. Now, what they were meaning before, you got to split this into 2 parts. You got to do the volume down here, which is disk method, minus the or plus the volume up here, which is the washer method. Okay, so this is just a plane region. You don't even need to do a disk. This is going to be a right circular cylinder. Okay, of radius 1 and height 1. Okay, you can just do that. You can just do that volume, pi r squared, where r is this. Okay, so that's just going to be pi times 1, that's going to be pi cubic units. Okay? That's that part. And then add to it here. So you don't need to do even a disk down here. You can just say that is a right circular cylinder of height 1. And then just do this. Being really lazy about it. Okay? So up here, the outer is going to be your 1, and the inner is going to be your, okay. Now here's where you run into problems. Because we're revolving around a vertical axis, we're going to be taking a delta y, but that means you need to get this in terms of y, which would mean solve this for x, and that gives you in terms of y. So you'll subtract 1 for both sides, so y minus 1 is equal to x squared, then take the square root of y minus 1. But you don't need to do plus or minus. The minus would be over here. We're only going to take this one and revolve it around this way, so you can just deal with the positive square root there. And that's where the square root of y minus 1 is the inner radius, and you're going to revolve that. All right. Okay. So, with that done, and frankly, here's something else you could do, and I don't know if they'll bring this up. Just do the whole volume here. Now it's going to be height 2, okay? Do the right circular cylinder there, you can do that, just be 2 pi, right? And then subtract from that this volume here. That to me would be the easiest way to do the problem, okay? And being lazy, that's what we do. They're going to do it this other way just to get you used to doing it, because it's not always going to be that simple. But that's all you got to do. And that would just be the washer. The disk method inside there, subtract that off from the other. So either way you do it, it's going to work out the same. In fact, the integrals are going to be almost identical. Okay? So for the region shown, the outer radius is simple. R is equal to 1. Okay, they're going to do it this way. Okay? There is, however, no convenient formula that represents the inner radius. So you have an inconvenient formula. Okay? You take what they gave you here and solve for x. Okay? And that would be but the x value, looking back at this, the x value here is your radius, right? That's the inner radius, okay? So that's what we're going to subtract off. So you solve this right here for x, and that gives you this, okay? Okay. And that gives you your little r is square root of y minus 1. Okay? Now, oh boy, did they come about doing this in a really strange method, but it's right what they're doing. Your lower part of that, the inner radius is 0, and the upper part is square root of y minus 1. Never would have thought of saying it like that, but you certainly can. And then you do a 1 squared minus 0 squared, which is a really difficult thing. They do it a really difficult way. This part makes sense. There's the outer one minus the inner one squared. Okay? So this is just going to be your pi, which we've already determined. And they carry it through to gory detail. That's going to be pi. Okay? But this one, okay, when you square this, you get, okay, 1 minus this thing squared would be y minus 1, but it's a minus y minus 1, so this would be 1 minus y plus 1, which is then 2 minus y. They did a big jump to get from there to there. Not showing you how, but it's pretty simple. Okay, that's why it's 2 minus y here. Okay, and then this just comes out pi. We did that in our head, and this will be minus antiderivative Why am I letting them do the work? We ought to be doing, we should have done this, I'm sorry. Brain malfunction here. Antiderivative of 2 is 2y, antiderivative of y is y squared over 2. And then this is your integral there. And it's evaluated from 2 to 1. That would be pi from here plus plugging in here, that gives you 4. Minus 4 of 2 is minus 2. Plugging in the minus here, that would be a minus 2. And plugging in here, you get a minus minus is a plus 1/2. This adds to 0, so you're subtracting half a pi. Okay? So pi minus half a pi is pi halves. No, pi plus half a pi is 3 halves pi. Okay. What I was doing in my head was, if we had done the whole cylinder, that would have been 2 pi here, and then subtract off the half a pi, that would give you 3 halves pi. That's really the simplest way to do it. Is do the whole cylinder, and then subtract off just that inner part, and you get 3 halves pi. Okay. So, sorry, I should have had you do the work there. I don't know why I let them do it. So 3 halves pi. Any questions on that? I know I skipped too much there. Need it seen a little slower? Want me to go back and do it? You okay? All right. Now, notice that the first integral represents the volume of right circular cylinder of radius 1, height 1. The portion of the volume could have been determined without using calculus of that portion. Okay. Which I said I wouldn't have even bothered with calculus. All right. Now they're skipping example 5, which is a manufacturing example, which sounds like it could be real-worldish. It is found at larsoncalculus.com for an interactive version of this type of example. A manufacturer drills a hole through the center of a metal sphere of radius 5 inches. So you're starting with a metal sphere. I don't draw spheres very well. Okay, there's a metal sphere, and you're drilling a hole through the center of this metal sphere of radius 5 inches. So this original sphere has a radius of 5 inches. Okay? The hole has a radius of 3 inches. Now they draw it horizontally. You could have drawn it vertically. So here they're drilling a hole. So this is disappearing, and this is disappearing. So you have the cylinder missing in the middle. Okay? Now. Okay. And this has a radius of 3 inches. Okay. What is the volume of the resulting metal ring? Okay. Now, if on first glance you think, well, let's just take a volume of a sphere, that's going to be pretty simple. You don't need calculus for that. Minus the volume of a cylinder, you don't need calculus for the volume of that. That's not going to quite do it for you. Okay, I see your head shaking. Why not? This part here isn't the same. Okay? If you extended this out here, you're taking off too much. Here, you're not taking off enough. So now you're going to have to use calculus. Okay? And now I wish I had drawn this line not where I drew it. So I'm going to erase it and draw it here. Okay? So it comes out right at that point of intersection. Okay? Because guess what? We're going, and this is my 5 inches here. Okay? And this is my 3 inches there, and that's supposedly drawn from the center. Because we're going to need this length here. because you're going to be integrating from double from here to there. So you're only going to go that far because there's nothing here anymore. You drilled that away. So there's nothing out here. You don't go as far as 5 inches here. So you can do this. Anyone want to make a guess of what that length is? Can't, right? Angle here. 4. It's a 3, 4, 5 triangle, isn't it? One of my favorite of all tricks. Okay. So this now, and let's call this, oh, I don't know what to call it. Let's just call it X. X max is equal to 4 inches. Okay. Why not? So make our y-axis come through here, your x-axis come through there. And now indeed you are doing the volume of the sphere minus the volume, well, the volume of that curve minus the volume of the cylinder inside. Okay. So, what's your outer radius here? Now this time when I'm talking radius, I'm talking about this. Here's your delta x here. Not that I'm going to use that delta x particularly. I'm not. But I've got too much drawn over there. Ooh. That's not at all what I wanted to draw. It's this here. The outer radius is up to here, okay, and the inner radius is fixed at the 3, okay? So there's your delta x. What is this height here, where it intersects the top of the sphere? At that point. Now, actually, really what I want is this over here. But I've got it too messy, but we can use that representative there. What is the okay. Here is, I'm going to draw this back in here again. Here is the outer radius is to here. Now, I wish I had this over here where, in fact, I'm going to draw it here. It's going to be messy and crowded, but the outer radius here is, if your x is from here to here, this is your x. That's x max up here. This is your x here, and this again is 5 there. Then the height of this thing, the outer one, is what? Again, Pythagorean, but not as simple this time. The capital R is the square root of it's basically your y value here. What would that be? But this is x and this is 5. It's really gotten messy now, hasn't it? Right angle here, okay? Here's your x. The y is what you're looking for here. There's your r. And this hypotenuse here is 5. Because from the center to whatever point that is still your radius of 5 on the sphere. So what would this height here be? The total height of this sphere.
5.
Okay.
Square root of 5 minus x.
Square root of?
5 minus x squared.
Okay. 5 squared, which is 25, minus x squared. By that? Yeah. That's what you were saying, right? Thought so. Okay, yeah. Okay. All right. So there's your outer radius. Your inner radius is simple 3. It's always 3, okay? So your little r is 3, okay? So, what is your integral? The volume is, help me, pi, the integral from,
0 to 4.
okay, let's make it 2 times 0 to 4, right? Because it's going to be the same one side or the other, it's perfectly symmetric. So 2 integral 0 to 4, because that's the maximum that's going to go out here. What goes in here? 25 minus x squared. The square root of that squared will just be that, right? Because the square undoes the square root. Minus 9. Perfect. And that's times dx, because your little increment is dx. So the volume here will be 2 pi times the integral from 0 to 4, because that's the x limits here. Now, 25 minus 9 is 16 minus x squared dx. That will be 2 pi. Antiderivative of 16. 16x minus x cubed over 3, evaluated from 0 to 4. So this will be 2 pi times 64 minus 64 thirds. Minus 0. I did the 0 part, okay? So basically 64 minus 64 thirds is 2 times 64 thirds. 2 thirds of 64. This is 1/64 minus 1/3 64th. That would be, so it'd be 2 pi times 2/3 times 64. That's the lazy way of doing it, okay? And that will be, goodness gracious, 28, 256 pi thirds, I think. 256 pi thirds. Excellent. They got it right too. All right. Any questions on that? Lots of construction lines there, and I'm sorry it got so messy. But you need to figure out what the x is, knowing that length, and okay. You don't need to know what x is. X is going from the center to out here, 0 to 4. So that, you know, that's the x value here. In terms of x, then this height would then be the square root of this squared minus that squared. So that's where that came in. And then the rest of it is fairly straightforward. All right. Any questions on that? Whoa. Let's see. No, that's example 5. They don't have that. So, all right, to erase? Okay. All right, solids with known cross sections. I'm sure I know what this is meaning if I read and figure out what it's about. With the disk method, you can find the volume of a solid having a circular cross-section whose area is A is equal to pi r squared. That method can be generalized to solids of any shape as long as you know a formula for the area of an arbitrary cross-section. Some common cross-sections are squares, rectangles, triangles, semicircles, trapezoids. I guess it goes on and on and on. What in the world are they talking about here? What if it's not a revolution? It's just a solid, but you know basically its structure, you might say. Okay, for cross sections of area A of X taken perpendicular to the axis, the volume is the summation of those areas times dx. Okay? Now, if I can figure out a three-dimensional graph in 2 dimensions, it sometimes gives you problems in trying to see what in the world they're talking about here. Okay? Here we have a curved surface here. We don't have any clue on what the curve is. It's not necessarily circular. It could be any kind of a curve here. But your cross section is, if you're doing your dx's, because here's your x-axis, your cross section is going to be, it's rectangular looking here and there, but this is not rectangular looking. So I don't quite see how they call that. Now, unless this was a sphere, okay? If that was a sphere, yeah, you might be able to do that, but it still doesn't quite make sense. So you could maybe estimate it as a rectangle. Let's just read on and see what they're talking about. That would be difficult to do, I guess, is what they're saying. But if you did the rectangle, the same curve this way, hey, that ambiguity is gone because you don't have this curved piece as part of your deal. You're going to be integrating over that, so you need to do a dy here, and look at what you got there. At worst, that's a rectangle. It may even be a square, but it won't be a square. It will be rectangles. It looks sort of like a square, but it's not. So you're taking your dy. This would be almost impossible to figure out what the area of this thing was. But doing like this, I can do a rectangle, okay, and relatively easily, okay. So then that identifies what choice you take. So this is not a thing of rotation across an axis. It's some sort of a shape that you've got, but you're still going to do something like a disk method, only it's not going to be a disk anymore. It's going to be some other shape. Okay. So this would be miserable to try to do it by the dx's doing dy's. That would be a lot easier. Now, I say that, but then we've got, now that I look at this, this also looks like a curved, I hadn't noticed that before, it looks curved here too, which could still be, it's not problematic there, but you know, okay, what you have to do then is be able to figure out, since you've got a delta y here, you need to get these dimensions, your width this way and your height this way, in terms of y, so you can integrate with respect to y. So you're going to need to know something about this surface here in terms of y, so you can solve for y here. And if this is indeed a curve like this, you need to be able to calculate that. Now, for the life of me, I don't see what your y is equal to c here, what that is even talking about. Y is equal to d, that makes sense here. Looks like it's y is equal to 0 here, if that is indeed the x-axis. So maybe c is equal to 0 is what we're saying. But that part of the figure doesn't make a lot of sense to me. But maybe I'm just not seeing it well. I guess they're saying the generic form here, what if that wasn't y is equal to 0, they've just shown something parallel to the x-axis. Or that part back there isn't included, it's going to start here and go to there. So that would make sense, I guess. Okay. So here's example 6. Find the volume of a solid shown in this figure. The base of the solid is a region bounded by the lines f of x is equal to 1 minus x over 2. So in the xy axis, 1 minus x over 2, that's just when your f of x is y, by the way, so y is equal to 0, then 1 is equal to x over 2, so x would be equal to 2. And sure enough, that's where it comes to here. And when x is equal to 0, y is equal to 1. So that would be that. So there's a line, y is equal to 1 minus x over 2. Straight line going between 0, 1 and 2, 0. Okay. That's that one. Your g of x on this side is minus 1 plus x over 2. You can do the same arguments here when g, let's see, when g is equal to 0, then x over 2 is equal to 1, so x equal to 2. So sure enough, you're at the same point there. And when x is equal to 0, g is minus 1, so you're here. So that's the on the xy plane, those are the two lines of intersection, two lines that form the base. And x equals 0 will be back here. So that's your third. So here's your triangular base between those 3 points there on the base. Hard to say this in 3 dimensions because you got something going here. Now, okay. Now, either they've left something out of the description, yeah, okay. The cross-sections are equilateral triangles, okay? So they haven't told you what your z is here. They haven't even mentioned there is a z, okay? Because they're going to do it just in 2 dimensions here. But when they say it's an equilateral triangle, that means whatever your y values here, how to express that? The y value here plus that, so twice either one of these values here, but make them both positive. That's going to be one side here, and then you're going up in equal length here and equal length there. This is a weird way to express the problem. Cross-sectional, okay, equilateral triangles. So we know the base. We can calculate the base of that triangle. It's this minus that, right? Because it's the upper one minus the lower one. So that's the base, okay, of that triangle. Now, with that being an equilateral triangle, that means these angles here are 60 degrees, of course, right? Okay, so that means this height here is, and you know, this would be the square root of 3 times this length right here, because the sine of 60 degrees is, this would be the square root of 3 times this length right here, okay? All right, we may not need that, but we'll get to it in a minute. Okay, so that's all they tell us here. So we got equilateral triangles going back this way, each one of these. So you got a delta x here, and you got these, both your g and your f in terms of x, and the length of that base is this minus that. The width is your delta x, and what you got to do is the area of that equilateral triangle, okay? So I think we pretty much got it set up to do, okay? So that you've got to get everything in terms of x's. So you need, in terms of this measure here, there's your x, okay? That's going to determine this x, that everything's going to bound on that, okay? So your length here is f of x minus g of x. So your base of that equilateral triangle is f of x minus g of x, which will be 1 minus x over 2 plus 1 minus x over 2, which would be 2 minus x. Okay? That's the length of the base here, no matter what value of x you are. Going from 2, which would be a 0 length here, back here, which is x equals 0, that would be a length of 2. So yeah, this is all making sense there. There is the base of every one of those equilateral triangles. Okay? The height of the equilateral triangle is going to be root 3 times half that base, I believe it is. Okay? Because the height here, if this is a 60 degrees here, this is 1 minus x over 2, half that length, okay? And this will be root 3 times that. So it'd be root 3 times half of that, okay? Let me make sure I'm thinking right there. I believe that's correct. Let's see. If that was 1, okay, let's just, it really doesn't, okay. Let's take an equilateral triangle here. Okay, let's just suppose that is. Okay, so if this is 1, that's 2, this will be the square root of 3, isn't it? Yeah, yeah. So that's square root of 3 times half that length. Okay. So there is your height. So this times square root of 3 over 2. Okay. I think that's the area of it. Okay. 1/2 the base, which is this, times height. I think it's actually got an over 2 down here, so I think it's 1/4 of that. Okay, am I thinking right on that? Okay. The area of this triangle is 1/2 the base times the height. That's the base. The height is square root of 3 times half the base, and 1/2 of that would then be that. So you've got the square root of 3, the 1/2 from the area formula, 1/2, and then you got your half of this base. I got by taking this divided by 2, so I think this is the area of every triangle here. And then your dx is your thickness, so I believe that's what you go integrate that from 0 to 2. Does that make sense? I can convince you of it anyway, huh? So let's do the volume then would be root 3 over 4 times the integral of, let's go on and square that. What would that squared be? Bill told you last time, what would that be? Help me, somebody. 4 minus 4x plus x squared, okay, dx. And this is going from 0 to 2. X is going from 0 to 2. Okay, let's see what we get. Root 3 over 4. Antiderivative of 4 is 4x minus 2x what? 2x squared plus x cubed over 3, evaluated from 0 to 2. So that is root 3 over 4 times, let's double that, that would be 8 minus 8, is that right? Believe so, plus 8/3. Okay, that goes to 0. 4 will go into 8 twice, so it's 2 root 3 over 3. Could that possibly be true? Oh my goodness, look at that. It is. Okay. 2 root 3 over 3. Okay. Takes some geometry. It takes some trig. It takes all of the tools in your tool belt. Okay. To figure out what the calculus is the easy part. Figuring out the relationship between all those dimensions, that's the harder part. Okay. And you need to know your relationships of your, in this case, your equilateral triangle. Make sense? Okay. Let's see how they do it. Okay, the base and the area of each triangle's cross-section are, the base is 2 minus x. We got that. The f minus the g. Okay? The area, oh boy, there's the area, of course, everybody knew that, right? But how you got it, and that's what we used, but the base is that thing, okay? The height is pi thirds over 2, square root of 3 over 2, so times the base. Square root of 3 over 2 times half the base, and that's where the over 2 and the 1/2, that's where the 4 comes in. Square root of 3 times the base squared. So that is true, but that's not something I think that's intuitively obvious. They seem to act like it is. Okay? But anyway, that's what you do. So you just, now that you know that base, at that area, that's what you integrate. Okay? And that would be an integral from a to b, which in our case is 0 to 2. And I would never put the square root of 4 inside, bring it on the outside. Now, okay, interesting math here. They're doing basically a chain rule type situation here. To me, it's easier to go on the square of that and do it. They're doing the integral, okay, take this on the outside. And the integral of this would be 3 times this over 2, and that, this cubed over 3, I'm sorry, that's what I'm trying to say, okay? And then, the chain rule part of it would have a minus sign. That's where the minus shows up here. Now, I never would have thought of doing it this way, but this is correct. When I first looked at it, I said, where did the minus sign come from? It's because they did this whole entity here. And with the chain rule, you have to introduce the minus out here. And now you plug that in. And they don't even show how they did that. But sure enough, that will work. Because when you plug in the 2 here, that's 0. So that all disappears. When you plug in the 0 here, that gives you this, but you're subtracting this part, and that's where the minus sign comes in to go back and make it positive again. So this would be 2 cubed. Yeah, 2 cubed is 8 over 3. Okay. The minus, because you're doing this, that wipes this out. Square root of 3 over 4, 8 over 3. Gets the same thing, but I wouldn't have done it either of their ways. But maybe this, if this makes more sense to you, do it that way. Whichever way makes the most sense to you, go for it. Now, they're leaving off example 7. Okay, so let's back up and do example 7. Now, don't let me run over. In fact, I'm awful close to running over, am I not? Okay? I have a feeling we're not going to have time to finish example 7. Do you want to make a bet? Okay. Don't think it's going to happen. So let's just stop there, and we'll pick up next time with example 7, which just happens to be where I left off the last time I taught this, or sometime in the past. Homework exercises in 7.2, we're almost finished it, but not quite. Do either 5 or 7 or both. 5's they're both at Calc Chat, 5's at Calc View. Do any of the, either 9 or 11, they're both at Calc Chat, 9's at Calc View. Do either 13 or 15 or both, they're both at Calc Chat, 13's at Calc View. 17 or 19 or both, they're both at Calc Chat, 19's at Calc View. And by the way, even if you don't have, by the way, I don't know if you figured this out yet, you probably did. Even if you're not going to use the book, but if you want to see the type of examples, you can go to Calc Chat and see the problems. Of course, they show you the answers, which is bad, but you see the problems that I'm talking about. And anyone can go to that website. You don't have to buy the book. So I left off at 17 and 19, didn't I? Both at Calc Chat, 17's at Calc View. And do either 21 or 23 or both. They're both at Calc Chat. 23's at Calc View. Do any of the odds 25 to 31, they're all at Calc Chat. None at Calc View. 33 or 35, they're both at Calc Chat. Either 37 or 39, they're both at Calc Chat. 37's at Calc View. Any of the odds 41 to 47, they're all at Calc Chat. Now they say you need a graphing utility on this one. You might. I don't know. 49 or 51, try them if you want to. 53 is an exploring a concept. You can try that if you want to. They should all be at Calc Chat. There's a comparing volumes, 55, that should be at Calc Chat. Any of the odds 57 through, no, do 57, that's at Calc Chat. There's a manufacturing problem, probably similar to one we did, 59, that should be at Calc Chat. And then they talk about volume of a cone, 61, and using a cone, 63. I think those are similar to what we just did, but somewhere there you can stop. We'll pick up the rest of those next time. All right. That probably ate up just about all the rest of my time, but it's not. All right. Now, the good news, folks, next week we will have 2 classes, okay? The first 2 weeks, 1 class each. Too bad about that, but starting next week we'll have classes Mondays and Wednesdays. We do have are open for business on most Mondays, so we'll see you then. All right, good deal. In my last class, the first person actually turned in a research paper. For those who weren't here last time, if you turn it in the month of May, you get 2 bonus points. You only have a couple days left to do that. The month of June, you get 1 bonus point. The month of July, you just get your score.